All right. Obviously, I'm going to cut this part of the recording. So, welcome to our meeting. I'm going to talk. This is an interesting bug that I wanted to kind of dive into, an interesting topic to dive into, because I kind of wanted to pursue a specific bug a little bit, but also it is a kind of cross-cutting bug that affects two fundamental-ish things in the way that rustc works. So there's, we'll see how far we get. We may want to do another meeting, but it's kind of an interesting way to instruct. So I put a little rough agenda, if you're in the paper doc, and I guess I'm sharing it. I put a rough agenda here. These are the two things. So the first one is like how to deal with higher ranked trait bound like things and solve constraints like for all A tick A tick B or other similar things, and how we do that, how we kind of implemented that at a low level in rustc today. And this is something that I recently changed, and that's kind of the problem in some sense, the source of the problem. And then the second half is some details on how rustc's trait solver presently works, and how that interacts. And then basically the interaction of these two leads to, or how the interaction of these 2 points leads to number 57639. So that particular bug is a regression here. And the problem is, this is like a minimal example of it, but let me see if I can remember. Right, and I kind of laid out some of the things. What it comes down to is that the compiler is making a poor choice and forcing a for all requirement that is stricter than what is actually necessary. And it didn't used to do this in the older system. And I guess I'll have to talk a little bit about that too. So you have to sort of cover how we're handling regions, how we're handling trait selection, how we used to handle this situation to a certain extent, and why it led to a different outcome. Then we have to decide what we want to do. So let's dive in. So the first one, for the higher ranked trait bounds problem, I think, so there are a lot of different ways that we can get ourselves into, you could sort of derive these kind of constraints. So one of the simplest ways is that you could have like a type like this, right? And you might ask yourself a question like, is this a subtype of this other type? So what this says is I have a function pointer that takes a reference with any lifetime. And I want to know, can I use that function? Let's make it more concrete. I might have like somewhere I have a function pointer like this. And then I have another variable with a different type. And I want to know, is this assignment allowed, right? And that basically says, can X be assigned that type? And in order to do that, what happens is we have to, let's see, how does this, there's basically an algorithm for doing this. And the way it works is that when you see for all binders on the left, like on the subtype side, well, let me go to a more intuitive level. So first of all, is the answer yes or no? Should this be allowed or should it not be allowed? The answer is yes in this case. And intuitively, the reason is this function is able to accept a reference with any lifetime, or so it claims. And this type is a function that accepts a reference with exactly one lifetime. And that's kind of a subset, right? Because tick B is a lifetime, this function is able to accept any, so that should be okay. That means it can accept tick B. The other direction is more problematic. But we'll get to that in a second. So the way that this works in rustc today is when you're kind of trying to compute. You have two types, T1 and T2, and you want to know, is T1 a subtype of T2? And the outcome of this, in general, when we're asking this question in rustc, the outcome is either yes or no, basically. And the yes, if the answer is yes, we give back some what we call region constraints or lifetime constraints. Incidentally, I realize now I covered more or less exactly this in my recent blog post. So for all of you who are like following along on the internet and you feel like reading this blog post, it's kind of covering similar stuff. So hopefully that link is the right link. Yay, okay. So, right, so let me give a simple example before we get to the higher rank stuff. So if you had like ampersand tick A U32, if you ask this question, the result would be yes if tick A outlook, no, there's tick B. So basically, what we're saying here is, there's an important thing, which is that we don't, the subtyping engine, all of these tick A's and tick B's that I'm writing down are basically variables. We don't know what lifetimes they represent or what sets of loans in the Polonius terminology, but we just know that there's some lifetime. And so what we want to get out of this is what would be the constraint if we gave these variables, like map them to concrete lifetimes, what would be the constraint that must be satisfied for the subtyping relationship to hold, right? And so like a concrete example, and this all derives from the idea that a reference with a longer lifetime can be coerced to one with a shorter lifetime, because that makes sense. If it's valid for the longer period, it's valid for the shorter period. And so for this kind of case where there's no for-alls, it's easy, right? So our subtyping algorithm for that is like, if T1 is ampersand tick A U32 and T2 is ampersand tick B, well, that's too specific. If it's two references, then we can say we can kind of make sure that the T1 and T2 have to be subtypes of one another, so we can recursively do that, and that gives us back some constraints, and then we return like C1 plus tick A all those tick B. I don't know, that's kind of pseudocode. Does that make sense? So this is the sort of definition of subtype T1, T2. I'll map this to the rustc code in a second to make it more concrete, because I think that's important. But what about if T1 equals for all something, which is the case that we have here, right? For now, I'll make it specific to functions. It actually applies also to trait objects. And the answer is what we do if the thing that has to be a subtype, that's T1, has binders like this. Let's just say for all tick A right now. We make a fresh variable, inference variable. So the idea is it's valid for any lifetime or region tick A. So let's make a variable. We'll call it tick 0. Let's replace tick A with tick 0 in the function type, and then that's going to yield us like yielding a type T1 prime. And then let's relate T1 prime to T2. So to come to our example, we had for all tick A function and tick A U32. We would sort of replace and get a type like this. We replace the tick A with a variable tick 0. And why we do that is we say, hey, it was valid for all things. So we're trying to find, is there any value that we could give to tick A that would be would make these types compatible, right? And that's why it's an inference variable, because it's like, let's find a value that is compatible. So in this case, then T2 is just, T2 doesn't have any, or that. Then we have, like, you can imagine, this is not exactly how the code works, but you can imagine that there's I'm not sure how to present this. We'll do it like this. You can imagine there's some rule that says if you have a function type by itself without the for-alls around it, then you have to require that, first of all, the arguments have to be subtypes and the return type have to be related, more or less. And you notice I swapped the orders here. That's because of how functions work. They're so-called contravariant. Not that important to this particular thing. So that's how we get to our answer. So that will get us, so if we apply this algorithm to our original question, we'll basically wind up with having created, applied to our original problem, we have created a, we'll say the result will be like, yes, if tick0 outlives tick, or outlives tick b, right? Where tick0 is some fresh inference variable. And so sort of the result, I said that the result is like, oops, where did I say that here? That it's yes with region constraints. It also may make fresh variables as it goes. So it's kind of like plus fresh variables. And if this is the only use of tick0, like when we're going to come back later and do our inference process, we have to find a value for tick0 that works. In this case, the one answer might be tick b. That's like whatever tick b turns out to be, tick0 can, there's no other constraints on it, so it's not a hard problem to solve. This is only used once. Okay, that's sort of the easy part. But let's look at the other question, and this is where the universes stuff kind of comes in. So if we had, if we move the for all to the other side, so now we're saying we have some function without a for all, then we're relating it to this, but the super type has a for all. Here we probably want an error, because not necessarily, actually, we'll see that play out, but because whatever value tick a is, that's going to be a function that demands one specific lifetime at the end of the day. And we're wanting to use it as if it can accept any lifetime, right? And that's not necessarily valid. And the way we do this is where but we don't, before we replaced tick b, or we replaced the bound variable tick a with the inference variable, but that doesn't make sense here, because that would give us the same sort of thing. They were like, is there any value of tick b that works? And what we want to show is more like, does this work for any value of tick b? It could be anything. Not is there some specific value, but does it work for all of them? So this is essentially for all versus there exists is the question, right? And the way we do that is we introduce the idea of a placeholder and universes. And a placeholder is basically like a symbolic region where we say we don't really know exactly what this is. We know that it's different from all the other things. And if we can prove that it's true for that placeholder, then you could sort of swap in any region and it would have to be true for that too. So it's like a maximally conservative, right? And the idea of universes is that we say, okay, there's some set of names that are kind of global, that, like, if you think of lifetimes as, what's the right intuition to go for here? Well, if we use them as Polonius, then a lifetime is a set of loans, right? And those there's some set of loans where a loan is like a specific ampersand expression in the program. And those are kind of global names that any region could contain. But this placeholder name, this is like a special loan that's different from all the loans we know so far. And so when we make one of those special loans, we do it by creating we say that all the names of loans are in universes, and a variable is associated with a universe, and that basically describes the set of loans that it's allowed to contain. And so we start out with this. This is the root universe, U0. That contains all the global names that we know. I'll just do. By the way, switching from Mac to Windows is fine, except for the fact that the scroll bar goes like the old way before Mac decided to change it. And that's really annoying. I haven't gotten used to that yet. The new universe is like add some, let's say in this case just one, add one fresh name to U0. And so now if something is in U1, it can name all the things from U0, plus it can name this extra thing that was not nameable before. And these are a tree, so like U2 can extend U1 with one more name, but maybe U3 is a sibling of U1, and so it does not contain the name of U1 nor the name of U2, but it has some fresh name of its own, which they can't name. Good so far? Okay. So what we can do now that we have this idea is when we have a for all on the super type side, we can create a new universe, create a fresh universe that is a child or that extends the current universe. So let's assume we have some notion of the current universe U, and we make a fresh universe U prime. This has some, add some placeholder names, conceptually at least, into U prime for each region. And now, I can't type. And now we can replace the for tick B with these placeholders. So where we had like for tick B function ampersand tick B 32, we now have I'm going to use this bang notation. We now have a function that doesn't have any binders, but has this sort of placeholder region instead. And we want to relate, then we sort of relate T1 and T2 as before. So where we had, so if we go through our step, we would wind up saying, we were checking this in, let's say, in universe 0. And now we're checking that in universe 1, which contains this placeholder. And that gives us this result, which says, basically, this is true so long, oops, I have this backward. It's contrary. Let me do it one more step. This will be true if the argument types relate and they flip orders, and that gives rise to this region constraint, right? Which basically says tick A, whatever it is, has to outlive every region, like some region that we don't know, which it can't really do because we don't, or it can't do, I don't know, if you had some sort of empty region that's never valid or something, you could do it. But this is the point, like there's no region that is valid at some point, which is known to be outlived by every other region. So this is probably an error, or at least it's an error, let's say, if the function is ever called, because the reason that would be required is that, like, maybe you could infer that it's a function that's well typed as long as it's never called or something, but it's not that useful. I don't think we even support that. Okay, that's the kind of theoretical side of this. So you could view this constraint, you could sort of take it out of the universes and go back to the for all notation, and you could sort of see it as saying this, right? And that's sort of what how I described it in the blog post. But in the way that the compiler thinks about it, this is actually much closer. So maybe we'll dive a little bit into that now. But we really track the universes the way I talked about them, and we kind of don't ever bother to decode these constraints back to the more structured tree-like form. So another thing to note that's important is I described, like shifting to the implementation side of this. I described the universe tree as a tree, and it is. However, in the compiler, we only keep a single integer. So what we do is we kind of rely on the fact that we will never ask cousins to interact with one another. The only way for things to interact is by sharing an inference variable. I didn't get into all that detail. Suffice to say, it's enough to keep just an integer. So you just remember like the index, and if the index is greater, then you know it's a child, and if it's not, it's not. Let me try to make that a little more concrete. So I didn't show you this other case, which is like, this is maybe a good case to talk about before we move on. What if you had for-alls on both sides? We would like this to be true, obviously. This is the same type. So what happens is you do a combination of these things, but you first process the supertype. This will be important in a second. So we kind of started out with this, like in the universe 0, and we would first process the supertype and say, okay, we replace tick B with a placeholder, and then we replace the left-hand side with an inference variable. But this is the important part. Each inference variable has a universe, and so the inference variable tick 0 is in universe U1. Because that universe is taken basically from what is the current universe at the point where of this thing we're processing. And the idea is the universe that it's in basically says what are the names that it can be inferred to. So here, because it's in U1, it's allowed to take the value of the placeholder, right? So this will wind up with the same constraint we saw before, only instead of tick A, we got tick 0. So we'll get this constraint, just like we had before up here. But this is not an error now, because we can infer tick 0 to be tick A, and that's just fine. Okay.
I have a quick clarifying question. Are there, for what you're calling placeholders, the bang ones,
yep.
Can there be more than one placeholder associated with a given universe, or is that a one-to-one relationship?
There can be in Rust, because the order, basically you can have more than one region bound in a function signature. So like, it's actually a subtle point. It's kind of an interesting point. So like this function signature in Rust, which would be written more elaborately like so, it's not important whether tick A or tick B appeared first in this for all. And so we model that by having, like, we make one fresh universe with 2 names in it, and that's okay. But if you had a system like, this is like a subtle difference between some of the formal work, because often these are modeled as, like if you go to systemf or whatever, this is like a function from types. And then the ordering is, like, if you can partially apply it, you can say, I just say what tick A is, but I don't say what tick B is. It kind of matters, but that's all not really relevant to us. Anyway, so yeah, you can have more than one, and that's okay. So, okay. Well, I guess I'll look a little bit at the code. So what I'm going to do now is share my, share something different, if I can figure out how. I guess I will new share. No, probably I should stop this share first and do a new share. Okay. Did you all see this? I want it bigger. Why is it not big? Stupid Windows. Why? Okay, we'll settle for that. Can you all see that? I don't know how to make the font bigger.
It's big enough.
Okay, good, because pressing the keys I would expect to make the font bigger did not make the font bigger. So it's clear. Let me get what would be a good one of my workspaces here? This one will do. So let me walk a little bit through the code. So we got, and we'll try to map these concepts. First of all, the regions in rustc are represented, the lifetimes regions, represented by this region type, right? Which is just so region is just a region kind that's put into an interning pool, like memory allocated in an arena. And you can see it has various variants. The one I wanted to call your attention to is this placeholder here. So if you have a placeholder region, this is what it would be represented as. And what is happening now? Okay. So if I jump, what is placeholder region? Yeah, it's taking me some time to get used to this new thing. I didn't anticipate this problem. How do I get, okay.
It's okay, it forces you to operate at R speed.
Yeah. Okay. I don't know what's happening now. I'm kind of irritated. For some reason, I can't seem to issue commands to Emacs. Why? Okay, we're going to do this slightly different way. Let me stop this sharing. And I'm going to share instead. This, you should see my web browser now, right? We'll do it like this. So, do you see, everyone sees, I hope, yeah. Right, so a placeholder region, this is just, I don't remember what file this is in, this is the annoying thing, but it's basically just a pair of, there we go. It's this placeholder type, which somewhere is defined, I don't know where, there it is, which has a universe index and a name. So Aaron, to your question of can there be more than one thing, this is basically why. You might have one universe and you would have distinct names. So that's how a region is represented. And then actually region inference, let's see, is broken up into a couple different things. I'm just going to jump to some file. But the relevant code, so if you go into the infer directory, this is our whole type inference set of code, right? And the bit of code I'm most interested in right now is this region constraints module. And what that contains is basically the code to collect these constraints. So what I was writing in the document, I wrote like this, tick A, tick 1, all that stuff. This is how we represent those in rustc. And it's also where we track the set of region variables. So it's this big struct. It's got a lot of stuff in it that's not too relevant here. But the most important thing is for each region variable, we have some information. This maps from the vid, which is the variable ID, to the information about the variable. And then there's a struct called data, which has like the set of constraints. And I'll get to that in a second. So a region variable info is really not a lot of stuff. It's basically the origin. This is for diagnostics. This is like, why did I make this inference variable? It doesn't affect the type system rules in any way. And then the other one is the universe that we created the variable in. And so when we make a new region variable, you just give those two pieces of information and it gets stored. Now the region constraint data, okay. Where's that? There. So this is a big struct. Not all of which is very important, but the important part is this field here. So it's a B-tree map only because we want to detect duplicates, but it says it has a constraint, and then the value is why did we create this constraint? That's again for diagnostics. So if we look at this constraint, this is one of these tick A outlives tick B. The 4 variants are all the same. The only difference between them is, in which case this is 2 inference variables. This is an inference variable and something that's not an inference variable in both directions, or 2 things that are not inference variables, which happens to be convenient. So you see what I meant about we don't track the for-alls and all that stuff. We just track which were the 2 variables, and then we know what universe the inference variable was in, and we know what universe the placeholder is in, and we can kind of figure out all we have to know. And the way we do inference, for now, I'm going to ignore NLL for a second because it's not actually relevant to this. It's sort of easier in the lexical. So this is the old region solver. But NLL has a similar character for this purpose. The way we do region inference is, that's all in this module called lexical region resolve. And it's basically a really simple process in which it's right here, infer variable values. And what it does is, it's all in this function expansion. The idea is that for each region variable, we start out with what its value is. And we start out, I think, with empty, meaning that it's not usable anywhere. And then we keep growing it in response to constraints. So if you have a constraint that says, like, the variable must outlive tick static, then we will say, okay, it must be tick static. But that's a kind of an extreme point because you can never get bigger than that. But if we say the variable must outlive, so this is lexical region resolve. So it might be like, it has to be as big as this statement, this part of the code, right? And then we would grow it to that statement. And then if it has to outlive the neighboring statement, then it has to get big enough to encompass its current value, which was statement A, and the neighboring statement B. And the only way for it to do that is to jump up to the whole enclosing block. So it would become the closing block, and so forth. That's pretty easy, but that's all assuming you're kind of in the root universe. So what we basically do now is we extend for, well, what happens if it has to outlive a placeholder, right? So if it has to outlive all the regions. And so here's the expansion code. It does this iterate until fixed point. So this is just going over and over again and recursively growing things until we reach a fixed point where all the things are satisfied. And then we see, so I should point out, this was written in the old days. So you see how it says sub here? I've been showing the constraints as tick A colon tick B, meaning tick A outlives tick B. These constraints are actually stored in tick B less than or equal to tick A form. So they're the same constraint, but reversed, because that was how I thought was more natural at the time. So yeah, so that requires a bit of a mental shift. But this is saying, like, if you have some region variable which outlives some specific region, this is like blah, 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 it's going to call this in function expand node. So essentially in this, what we're doing here is we're trying to get some specific region, and some variable, and some specific region it has to be bigger than, and we're going to pass that to expand node, which is going to make the value of that variable be big enough to enclose its current value plus this region. And then we're going to do that iteratively. I forget what this other stuff is, but not important. So here's the function expand node. And it takes the region, the variable that has to be bigger than this region when it's done, and some data. We'll figure out what that is. I think that's like this is like some other information. Okay, yeah. So this is, I think this basically contains the current values of all the variables, if I'm not mistaken. Ignore the givens, please. I'm like embarrassed that that code is still there. We'll come back to it. It's not relevant right now. So this being the givens. Don't look there. Don't look where my mouse is. So the so what happens? We look what is B data actually? Let's take up here. Oh, I see. So B data is actually the value for this exact variable. That's what it is. It's not the set of values for all variables. It's the value for this particular variable. So we look at what is the current value, and either it's an error, meaning that we already found that for some reason there was an error. In that case, we can just ignore it. Or it has some value now, which is this current region, right? And then we can check, this just checks, is the current region already the same as the region that it has to outlive? Then that's like saying tick A outlives tick A, so it's fine. It's a no op. That's a performance optimization. Otherwise, we find, so lub concrete region says, okay, we got two exact scopes in the lexical system. Let's find their least upper bound. Let's find some scope that encloses both of them. And if that's the same as the value we already have, then we're done because we didn't need to grow. We already included the new value we have to include. Otherwise, and here comes the placeholder code. Otherwise, let's look at what universe this variable was declared in. And let's look, if the value that it has to take on is a placeholder, then we check if that placeholder is in scope for the universe. And if not, we make it be tick static. Let me take this back now to the paper, Dropbox paper, to try to explain that logic. So if we come back to this case, actually let me give a different case. Which was the case? Well, yeah, this first case. So this is the case where, no. Which case do I want? Neither of these cases, none of these cases actually fit what's happening here. Is that right? I think I want a slightly different case than what we have. Because it would, okay, right, I want a different case. Let's do this case. Okay, so we always looked at parameter types before, but I think the case I want is actually will rise more easily with return types. So if you work this through the algorithm that we said, we're going to replace, oops. We're going to replace, so on the left-hand side, we have, I'm writing tick 0 here instead of tick A. I'm just saying there's some inference variable that we've created in the past, and it's part of this type. And so we don't really know what it represents yet. And that's really what the tick A's were before, but I thought maybe it would be clearer this way. And so we're going to replace the placeholder with a fresh universe. We're going to replace the bound region tick B with a placeholder in a fresh universe. And then we're going to relate, and now because these are return types, we don't swap the order, they're covariant. So in order to relate these two function types, we'll relate their return types. And so we'll wind up with a constraint like this, which says this variable has to live longer than this placeholder. And so expressed in our in the notation that the lexical solver is using, it would be like that, right? And now this is interesting because we're now when the solver runs, it's trying to change the value of tick 0 to be something that lives, like it doesn't matter what it is as long as it's longer than this thing, but this thing we don't know exactly what it is. So there are two options. Either if tick 0 is in an appropriate universe, like if it were in the universe 1, we could set its value to be the placeholder itself. That would be great. But if tick0 is not in that universe, there is still another option. It could equal tick static. And tick static is known to outlive all the things. So that would be okay. So that's what this code is doing, right? So it's saying, assuming that I can't name it, then I'm going to basically, lub is the least upper bound is going to be assuming you can name the placeholder. And so this is saying, in the case that I can't, let me reset that. I have to grow even further. I have to grow all the way to tick static to make this be satisfied. And then we can just set the value to whatever this least upper bound is, and it should be okay. And so the kind of interesting thing about this is that, in a sense, you don't get often an error. You kind of get success, but you get just a really, really big region that may give other errors later. Like maybe because you were inferred to tick static, you now hold a borrow for a really long time, longer than you expect, and stuff like that. And I don't know, there's also the reverse error. How does that play out? I'm not sure. I think that comes to do with the least upper bound, right? So sorry, if we go back now to my original example. So here I put it in the return type. But if you have the placeholder, like in this case, the placeholder was in the parameter type, we wound up with the placeholder being the sort of lower variable. Or sorry, it becomes the outlive thing. Then that winds up reporting an error through a different path, because when we're doing the region solving, we're only interested in growing the inference variables. We try to make them, so we only basically care if the inference variable is in the left-hand side, if it's the bigger thing that we can make bigger and bigger and bigger. And then once we've found a value that's big enough to satisfy all the places, then we go back and look for the constraints where it appears in the right-hand side. Was it still small enough to satisfy? So we're finding like this is the smallest value that will meet all the constraints, and maybe even the smallest value is too big. In that case, there's an internal contradiction. And we do that. Let's see, function dot. Okay, sorry, another Windows compatibility thing where some key I press causes like a lot of stuff to fly up in my face, and makes also sounds in my ears that I hopefully you guys can't hear. It's driving me a little crazy. Okay, so right, so the expansion is this phase where we're growing all the things to be the smallest values that satisfy the constraints, and then the collect errors and collect var errors is where we go back over and say, are those too big? If so, let's report an error. And that's where this placeholder, the fact that this variable had to be smaller than a placeholder, and we don't know what the placeholder is, would fail.
Nico, why isn't it possible to record the error when you make the region like really big? Like, why do we have to go back over it afterwards?
It's not necessarily an error that it grows to be tick static. There are examples where that will type just fine. So if you recall, I could give you one if you want. But if you remember from the very first thing we looked at, I said something like, we'll make an inference variable, and it's not going to be constrained anywhere outside of this like subtyping relationship. So all the constraints arise from there. Then it may well be that tick static is a perfectly valid value for that variable to take on. Or maybe it just is a valid value.
Okay, that makes sense. Thanks.
Somewhat related to that, so in the sort of case that there is ultimately an error, does the compiler do some work to sort of, so I can imagine like this picking tick static thing, if the code is ultimately erroneous, you could get a very confusing message where something is claimed to be tick static and it's hard to understand where that's coming from. Is there some logic to try to like catch that case and explain it?
Yes, there is. So there's this module called Inference Error Reporting Nice Region Errors.
I love that.
And one of them is called placeholder error. And indeed, this is the way this basically works is when you get an error from region inference, it's kind of like, here's a constraint I couldn't satisfy. It's kind of the shape it takes. And then the job of the nice region errors is to like look at that constraint and try to see if we can categorize it into something for which we have a tailored error message. Try to take a guess as to what's going on, basically. And so this particular one tries to detect if it came about as a result of a placeholder conflict. And there's various scenarios. You can see it goes through a reasonable amount of effort to make a nice message and say things like, you know, this thing would have to be implemented for this type for any 2 lifetimes, but it's only implemented for this type for some specific lifetime and stuff like that. So yeah, we put a lot of effort. Actually, this transition to universes was accompanied with we never did have nice errors for this case, and so I tried to like do that at the same time. And there are some cases that's still a work in progress. There's still a few. I think we fixed all the major regressions. Maybe there's one left. LQD's been working on that, kind of extending this to cover more and more cases. But.
So, and then one other thing, and this may be clear to everybody here, but just in case, just trying to think about like all of these constraints we're trying to put in place with universes, right? So I think the case we care about is, it's basically about nesting of exists and for all. So if you're saying that there exists something such that for all something else, something happens, then that's why we can't allow you to pick that outer thing to be whatever placeholder you're using for the inner thing, because you're trying to show that it works.
Yeah, so I debated whether to start with this, and maybe I should have, but anyway, too late now. But let me, because we only have a few minutes left anyway, so we're not going to get to the rest of my agenda. We'll have to schedule a follow-up meeting. But this is good. I think now that I've walked through all of this with you, we can look at the pure logic side, which is like what basically what Aaron was saying is you could have a couple of, you imagine A and B are variables of any kind, essentially. You could have a constraint like this that says there exists an A such that for all B, A equals B, or you could have a constraint like for all A, there exists a B such that A equals B, right? And this latter one, this is like just fine, right? So obviously, for all A, there is some B that is equal to A, and that's just A, at least if you have a suitably, I'm sure there are logics where that's not true, but anyway, in the cases we care about. But this one, not so good, right? At least if you want to be general, then you can't say that for all B, there's some A that equals it. The only way you could say that for sure is if there's, like, you know something about the domains and these variables, there's only exactly one value, then okay, sure. But, so, or rather, yeah, you see what I mean. You can't pick some A and then know that it's going to be equal to all the B's, unless there's exactly one B and one A. They're the same. And right, and so this would map out to basically A being in universe 0 and B being in universe 1. And hence we get a conflict, but in this case, A, or rather the placeholder is in universe 0 and the variable is, or rather, sorry, it's in universe 1. The placeholder is in universe 1, but the variable is also in universe 1. And this actually is the framework by which I think I can explain why we only have to keep a single integer instead of this whole tree hanging around. Which, roughly speaking, the idea is that we process these constraints by like walking down this tree. And so they don't directly communicate to one another in some sense. So the only way that a value, like here's a situation where you have for all B some stuff and for all C some stuff. And these are two siblings now. B and C are two different universes. They can't communicate. But the only way that like solving the stuff in this first half could have side effects somehow that are like visible to this other half is if it changes the value of A. It's the only thing they have in common. And A is already in the root universe. So any value that A could have is some value they can both name. So long as we don't allow, like, if the bad case would be like this, you know, if we were buggy, if our logic solver was buggy or something, it might say, oh, okay, A is equal to B, and therefore this is like saying B is equal, asking if B is equal to C or not. And since we've assigned this index 1 and we've assigned this index 2, and 2 is greater than 1, like it's okay because we think that they have a parent-child relationship when actually they don't. But that just can't happen because we would never allow A to take the value B in the first place. It would instead be tick static or error or something. So that's convenient because an integer is like small. Yeah, so that's the universe system. And I guess we should schedule a follow-up meeting to walk through the trait solver. And actually, that's sort of nice. This is enough for a day. All right. Thanks all. And
Thank you, Nico.
talk to you later.
Thanks.
Thanks. Bye.